Good afternoon. Welcome to the next talk in the CrySP speaker series on privacy. Our speaker today is Joel Reardon, who did his MMath here at the University of Waterloo in the CrySP group, and now is a PhD candidate at ETH Zurich. And Joel recently gave a talk at the Zurich Security Symposium just last week, and today we are delighted to have him here giving us an extended dance remix of that talk. You get to dance, right?
I put on my dancing shoes.
Fantastic. So let's welcome our speaker.
All right, thank you for the introduction. The title of the talk, if you can read it, is Secure Deletion and Flash Memory. And I'll be talking about some of my research I've been doing on how to securely delete data. So, as you may be aware, secure deletion is the security task of removing information from a storage medium so that it becomes irrecoverable. So that if later an adversary is able to get access to something that contains sensitive information, they won't be able to access the information that's stored on it. Now, the motivations for this can be varied. For instance, these devices, these smartphones, are equipped with many sensors, and one of the things they tend to do is record your location data in various forms over the day, and where you actually are throughout the day can be considered quite personal information. On top of it, it logs who you call, so not only messages such as SMS messages saying what you actually say, but also metadata around it, who's talking to whom, when you called them, and these sorts of things. Another interesting problem is that they tend to automatically synchronize their emails, which has the consequence that you end up putting data onto these devices before you even are aware of what this data is. And you may have received emails in the past that say at the end, this is considered confidential or privileged information, and if it is sent erroneously, you must securely delete it immediately along with all copies and notify the sender. And if your phone is automatically retrieving this and you can't securely delete it, then you can't fulfill with this email demand. And finally, of course, because I'm partially funded by Swiss banks, corporate data, bank data, all of course necessary. There's some corporate restrictions which may say you cannot take this data into a different jurisdiction. You cannot have information about customers or banking information and leave, for instance, Switzerland with this information on a mobile storage device or other kind of storage medium. How do we securely delete it so that these corporate actors can fulfill what is required of them by law? So as an adversarial model, of course, because this is a security talk, we need to consider who our attacker is. And secure deletion is not a new problem, so there's been a lot of research that has been done in the past. And I've divided up some attackers that seem to have a reasonable means of attack or can be actually seen in the real world, and divided them up based on their capabilities here. So at the top, we have what is called the user-controlled disclosure time. And these two situations would be an internal repurposing attacker and an external repurposing attacker. And this corresponds to, for instance, you have a storage medium, you have a computer, you're going to give it to somebody else. Internal repurposing would be, as a student, you give it back to the university gives it to another student. You're not too worried about advanced forensics or the other student dismantling the hard drive to find out analog remnants that might still be there. External repurposing considers this attack. So with external, it means you're selling your computer on eBay. You don't know who's going to get it. They can do anything they want. And as you can see on the left, I call them software attacks. On the right, called hardware attacks. I won't actually be talking about analog forensics because that's not my particular area of expertise, but just to sort of have an idea of where these attacks would fall in against the kinds of attackers you're thinking about. So for these two, for repurposing, it's actually a pretty well-solved problem. There's been already a lot of research, and thankfully NIST has a standard, so you don't even need to think. You can just say, I have top secret data on my flash memory. Oh, incineration. That's what I have to do to securely delete it. So it works because you control the time of disclosure. You say, I am going to give away my storage medium at some time, and I can do some extraordinary measure before this actually occurs. So I can do something like incineration or degauss the hard drive or completely destroy it and make it unusable if that's what the security requirements would say. For top secret data, the risks of leak would be too high so that you might actually just destroy the storage medium. So my research has been more focused on an attacker-controlled disclosure time. That is, you do not know when your storage media will become compromised. At some point, it will happen. And you cannot perform necessarily any extraordinary measure to prevent it or to prevent access to data on it that you wouldn't normally do as a matter of routine. So attackers in this realm would be considered theft. Someone just steals my mobile device. This is quite frequent. Not for me personally, thankfully, but I hear it happens in the real world. And the other two attackers, malware and subpoena, this is an even stronger attacker because here the adversary is also able to obtain your passwords and passphrases. In the case of malware, it's something running on your computer. It might just be able to see what the password is that you enter. In the case of a subpoena, here is a kind of a legal attacker, though it can exist, coercion can exist in other forms as well. And the idea here is that not only will the attacker obtain your storage media, they'll also be able to obtain any passwords or passphrases required to access the information. And if you think about the subpoena attacker, in the end, it's really the case that you have to make it that you cannot access the data yourself. Because as long as you're able to access it yourself, then you might be able to give away information under duress that would allow the adversary to access it as well. So as long as you cannot access it yourself, then you can never betray yourself when you're being tortured, which apparently is the goal. No matter what you say, you can't make it stop. So the secure deletion problem in general, so now we have this idea of the attackers. Why is it a problem? Why can't we just delete a file and then it's gone? So now this is pretty much the same repeated problem in almost every file system that's ever been made because it's such a wonderful, simple optimization, and who needs security anyhow? When you delete a file, the only thing that typically changes is that a flag is flipped that says, no, the file is not deleted, to, yes, the file is now deleted. The sensitive data, of course, remains in some form on the storage medium. And generally, at some later time, this extra capacity that could be used to store different data is reclaimed. The resources are reclaimed. However, at the time of deletion, it's just a very quick operation. Now this particular sector is free to be used for new data. This problem has been studied and solved for a class of file systems and the storage media called block devices. These have the nice property that when you overwrite a particular block on the storage medium, it will replace what was there with some new version of the data. And of course, there's many different spectrums to this problem you can consider, but in principle, when you want to delete some sensitive data, all you need to do is replace it with zeros. You go to all the locations where this data remains, you replace it with zeros, and then you no longer are too concerned. Now, of course, there's other factors to consider, like analog remnants, if you're familiar with overwriting it 10 times or so on, although that's been largely deemed as unnecessary for modern storage media. But these are more complications to this general problem. The idea is if it's able to overwrite in place some blocks of the data, then it's pretty straightforward to erase your sensitive data. You just perform this operation. Now, this talk is going to be focusing on log-structured file systems, which is a different class of file systems. And they differ from traditional ones that we may be familiar with in that it performs every update to the file system as an out-of-place update. It appends a new record to the end of a log. So if you look at the chronology of the file system, you could see, okay, first you had this piece of data, then you had this piece of data, and so on. In this case, when you want to overwrite it with zeros, what you can see is that the new version of the zeros is appended to the end of the log, while the old version of the data is simply marked as obsolete. It's no longer considered necessary for the file system. At some point later, it will be reclaimed as a matter of just saving storage resources. But for the time being, the new value will always be added to the end of the log. The old value will still remain, and there's no real secure deletion that will be happening for the old value. So I said I'm going to be talking about these kinds of file systems for this talk. The question is why? Who's heard of these log-structured file systems? Why would we be using them? Well, it turns out that for flash memory, this paradigm is ubiquitously used. And flash memory is, of course, ubiquitously used in portable devices, so it makes it quite a sensitive attribute for an attacker, a sensitive storage media that an attacker could easily gain access to by stealing it because you're always carrying it around with you. And you also have the additional problem that you're going to be using this log-structured file system. You'll never actually able to delete data in a guaranteed way. So why is flash memory so well suited to this design of file systems? And it comes down to the actual physical property of the flash medium itself. So here, I've divided this log structure device into 2 levels of granularity, just as flash is divided into. We have erase blocks, which have a size of 128K. And throughout the talk, when you see a rectangle like this, it'll be representing an erase block. These erase blocks are in turn divided into pages, and pages are 2K, much more reasonable. This is the normal size of I/O. When you perform a read, you may only read a few bytes, but at the storage medium, when you ask the flash chip to read, it'll read an entire page at a time. The way flash works is that it allows the cells of the flash memory to obtain a charge and store a charge, an electrical charge, even without any electrical power at the time. So this is unlike RAM or memories that require constant power to retain their memory. Flash memory can hold a charge and retain it without power, and it does this through a very brutal operation called erasure. Erasing is a high voltage operation that floods an entire erase block on the flash memory with electrical charge, and the result is that all of the cells in this erase block have a charge. This is the erased state. When you actually want to write to flash memory, you perform a write, which is a very surgical operation where you go and you pick which cells you want to have drained of their charge. And you can do this not at the erase block granularity where everything is given charge, but rather you can program a particular bit to say, this bit you can drain your charge, but the bit next to you, of course, you keep your charge. And the result is some have charge, some are discharged, 0s and 1s, and you have your storage medium. The catch is that you cannot program or you cannot write to a page of flash memory unless it's already in its erased state. And the erasure, of course, happening at the large erase block granularity results in some very interesting algorithms required to access flash memory. And in particular, you can't perform in-place updates. You cannot have written to a page and then write to it again. You have to first perform this erasure operation. Erasures are also a good metric for efficiency because they consume more power, they consume more time, an order of magnitude more than reading and writing, and they additionally cause physical damage to the flash medium in the form of wear. And if you're familiar with the concept of a bad block is just memory that's been worn out due to repeated erasure. So it makes for a nice efficiency metric. You have 2 solutions that are equivalent, and one does fewer erasures, then the one with fewer erasures will be preferable. Now there's a caveat to this, and that's that erasures should also be evenly leveled, preferably. So it's a bad idea to only erase one part of the flash memory while not touching the others because it reduces its longevity. By evenly spreading the erasures over the entire storage medium, you can improve the lifetime of the memory, and so it is recommended. So now I'll present a sort of naive approach to this problem of secure deletion. Here, on one erase block, we have some sensitive data that we want to delete. It's now obsolete. And co-located is some other valid data. Now, when we're writing to flash memory, the files that are written to, there's no real reason for their order. It depends on how they actually are being written to by the file system. And the result is that these erase blocks will just happen to have data for different files co-located in an arbitrary way. Here, an eclectic mixture of co-located data. So you can't guarantee that an entire erase block will always be empty and ready to be erased. You're usually going to have other data, other valid data co-located on it. And the way to then securely delete the original data that you want would be you find the co-located data that's still valid, you duplicate it somewhere else, adding it to the end of the log, and by doing this, you obsolete the old version, you make it obsolete, then the entire erase block can be deleted and your data will be gone. Now, this approach is actually used by all the log-structured file systems. The name of the procedure varies. Tends to be most often called garbage collection, which I'm not a big fan of because we're actually collecting non-garbage and moving it somewhere else. But for the interest in being consistent, I'll just call it garbage collection. The idea is that there's some optimization metric that says, I can garbage collect this erase block by only copying 1 page or only copying 2 pages. And that's generally the efficiency metric done in these file systems. What is the fewest amount of data that I need to copy in order to reclaim an entire erase block of storage capacity? When you're doing it with security in mind, then it suddenly becomes, well, now I have some sensitive data, I need to erase it at no matter what the cost. And if you're going to do it for every single time you erase a single page, you're going to be copying 63, for example, other pages to the end of the log just to erase one page on the erase block that contains this sensitive information. And if you start doing this every time you want to delete a single page, it's going to become woefully inefficient. You're going to be copying a vast majority of the data over and over and over throughout the entire file system and performing this expensive erasure operation too frequently for this to actually be usable. But this is the sort of naive approach that what is the minimum that we have to do in order to delete this data, and that is to execute this erasure operation. So you may be thinking now that the problem has been described of some possible solutions. So one of the ones that comes to mind is, well, we don't have to perform this erasure operation immediately. We could just batch it over time. We could wait for instance, a day and say at the end of the day, perform this expensive operation, maybe when the device is charged to power so it won't be consuming its battery. And it can go and clean up all of the erase blocks that happen to have some deleted data. Of course, this still has the problem that these deleted data can appear anywhere, so it could be a lot of erase blocks that you have to delete. But I will be discussing this possible solution in the first half of the talk. Another solution you might think is, well, we don't need to delete all of the files. We only need to delete the ones that contain sensitive data, because these are the ones that are very important. And in fact, there's some related work with this. The Linux file system offers a +S sensitive attribute in the extended attribute set that would allow you to mark a file as sensitive. Copies of it are made automatically sensitive. You can mark a directory as sensitive, and its sub-contents would be also sensitive. The problem I have with this approach is that from a user's usability perspective, it seems destined to not succeed, to fail in some way, to miss some important data that should be deleted but won't be. Because if we suddenly start requiring the user to think about, oh, do I want to securely delete this SMS or just regularly delete this SMS? And what does it mean to securely delete it? It's like, oh, you could have a shredder and a pen going through the text or something like that to give an intuition, but it's still demanding the user think about these things and why wouldn't I always want to securely delete? Oh, it might cause some wear. And what does that even mean? And as well, if we have a system where we're not always deleting all the data, but we're relying on the applications to remember to set the attributes correctly and offer the user the choice, it seems that it's just not worth the extra burden on the user, and it'll fail in a number of usability ways. What I would prefer in this sense is then to divide the file system into two partitions. One, of course, user data. All of the user data is put there, all of your emails, and on the other side, you have your file systems, your operating system. If you're working on Linux kernels, you can put the Linux kernel there. If you're getting mail from the kernel mailing list, it'll still be securely deleted, even though the contents of the mail will be posted to some mailing list. It doesn't matter. Anything personal will always be deleted, and you don't have to demand that the user has a concept of this, what needs to be secure and insecurely deleted. The third one is to encrypt each file with a key. So the idea here, and this has been proposed a number of times, is that you take a file, you encrypt it entirely, you put the key in the header, and then when you want to erase the file, you just delete the header. And this is simple and elegant. The problem is that it's not as implementable as it seems. For one, some file systems have a very vague concept of what is a file. In a shadowing or versioning file system, of course, it's going to be just a bunch of shared blocks. And multiple files may share the same blocks, in which case encrypting the entire file doesn't have the same meaning. And second, the problem then becomes, how do you delete a part of a file? And for instance, for a mobile phone, consider an SMS application. I find it unlikely that every single SMS is stored as its own file. And if the result is that in order to securely delete one SMS, I have to uninstall the application to delete all of my SMSs, then we're sort of back to this internal-external repurposing attacker, where we're performing an extraordinary operation once to completely remove all the data, instead of this more interactive deleting messages at the time when you want the message gone, but still maintaining the functionality of the phone against a more active attacker like a theft or a coercive attacker. The final possible solution, or one that had been proposed quite recently, was it comes down to the actual mechanics of flash. So as I described, these cells contain their charge, and when you want to drain a cell, you can have it lose its charge. Why not just go back and drain all the other cells that have the sensitive data? So we go back to where the sensitive data is, we find all the ones, we turn them into zeros, and we're not trying to write new data, we're just letting it disappear. Later on, the file system naturally will garbage collect the erase block, and we'll be able to let the file system behave as normal. The problem with this approach is that doing this operation, programming twice to flash memory between erasures, is forbidden by flash manufacturing standards for some kinds of memory and otherwise just strongly discouraged. And the reason is that it can or may cause bit error rates to neighboring cells. So data stored around where you're doing this multiple overwrite might get affected, have bit errors, and of course this is pretty devastating. The people who proposed this this idea originally did some research, and they found that for some kinds of flash memory, this concern is completely exaggerated. They couldn't even make these bit errors appear. For other kinds, they could actually make it appear quite reliably after one or two multiple overwrites, and conclude that for these kinds of memories, this approach wouldn't work. The problem is that the ones for which it wouldn't work tend to be the very modern, densely packed, large ones, not the very old ones. So we conclude that the problem with this approach is that it won't necessarily work going forwards. Flash manufacturers won't design chips such that an out-of-standard technique will continue to work effectively on it. We'd have to test the chips every time a new one comes out. So what do we want to achieve in this work? Well, we want to work within the specification of flash memory. We want a solution that is palatable, that might actually be used by manufacturers and integrated into hardware chips. We want it also to work with all kinds of memory now and into the future, no matter what happens in the technology. We want it to be transparent to the applications and users. We don't want the user to have any concept that their data wasn't being securely deleted before. We want them to think that when I press delete on an SMS, the SMS is gone forever, and not have to have this second notion of secure deletion versus insecure deletion. We want it then to be small. So with these goals, then efficient. Little use of memory, little use of space, little use of computation, and in the end, what's the best that we can do? So the contributions that I'll be presenting in this talk, first is user-level secure deletion, which is what can a user do immediately without changing their file system? What can they just put onto their phone right now without having special privileges, without rooting their phone? What's the best they can do in this very limited model to get some secure deletion? And then we'll present the data node encrypted file system, which is a general change to a file system that takes an existing file system and adds a component such that the result is a file system that provides secure deletion. And finally, UBIFSec, which is the full implementation of our proposal for the Linux flash file system, UBIFS. But first, user-level secure deletion. So what we did to originally research this problem was we looked at the file system UBIFS, which was being used as the main file system for the Android Nexus One phone. And it's a log-structured flash file system. So it behaves exactly as I described in the introduction. We modified it to report all of the erase block allocations. So whenever it would pick a new erase block and start writing data to it, we would log the time and which erase block it was. And this gives us an idea of the deletion latency. Because if an erase block is allocated at this point and it's allocated again at this point, any data deleted here will be securely deleted before it's allocated again, because it can only be allocated after an erasure operation. And similarly, we recorded all of the writing behavior. So every time we would write to a page, we recorded information about that to help us build a model of how the phone was writing to the storage media that we could then later use in our simulations. So here is a plot of the block allocations over time. On the x-axis, this corresponds to the experimental time. And on the y-axis is the space of erase blocks. So you can consider each row to be an erase block. And every time you see a black square, it means that that row's erase block was allocated at that time. The distance then between two consecutive allocations of the same erase block then corresponds to the deletion latency's upper bound. Now, the UBIFS file system has a cyclic approach to allocating erase blocks, which you may be able to discern from this figure. And what is interesting is that this leads to the hypothesis, well, if we increase the number of erase blocks that are available in the storage media without changing the rate at which the phone is being written to, we would then expect a similar increase in the x-axis, the time until deletion. So we did this in experiments, and this is exactly what we found. So for the particular phone, there was only 200 megabytes. Okay, so deleted data might stay there for a couple days. For a 2 gigabyte device, which is completely reasonable size, it would be over a fortnight that your deleted data just sits on the phone. Now these are the 95th percentile measurements. Of course, the 100th percentile was undefined. There's no guarantee that the data would actually be deleted. If it happens to be the only deleted page on an erase block, then the file system will always skip it in favor of any other erase block that has a little more wasted space on it, just as a matter of heuristics. And this also has the concern that if the phone isn't being used, then the data just stays there. You actually have to be using the phone, writing new data to it for this inevitable churn to occur. And so we conclude that this is a problem. What can we do about it? So targeting a user-level solution, it gives us very limited access. In one way, it's quite usable because anyone can just install it on their phone and then they have secure deletion. On the other hand, the only thing it can do is create and delete its own files. It can't interfere with other applications' files. It can't change the file system. Maybe it could call some ioctls if they happen to be around, but in this case, it's a very limited mode of access. But despite that, we have 3 solutions: purging, ballooning, and a hybrid of these both. So the first one, purging, is pretty intuitive. You just fill the storage medium. And it requires that the file system will allow you to do this, that there's no disk quota limitations in user space, and also that it provides the guarantee that if you completely fill it and the file system says, no more data please, I'm full, then there really is no single deleted page that could possibly be reclaimed through this garbage collection operation. And for the YAS file system, along with some others, these conditions hold true, so we're able to perform purging, and you can see on the far right, near immediate allocation of all of the erase blocks. This is because the file system is going through erasing every erase block that has some deleted page on it, and of course, the cost is that you have to perform this erasure operation quite frequently. In fact, unreasonably frequently for the 2 gigabyte device, to the point where it actually takes a noticeable amount of time that it's just sitting there deleting these erase blocks. But from a user level perspective, this is really the best that we can do. There's no other way from user space of guaranteeing the secure deletion of data, except that, and this follows from a simple lower bound or worst case argument, that if there's one page that's not deleted, we have to conclude that it's the most sensitive data is stored on this page, and there's no other information that we're going to get from the file system about it. So our second solution is called ballooning, and this works by continually occupying some fraction of the storage media's free space with junk information. So the idea here is that when the free space threshold, which is just some desired threshold for how much free space should be made available to the file system, when it drops below, when the actual free space drops below this threshold, then junk files are deleted to return back. And of course, if it goes in the other direction, then new junk files are added. And the goal is to always keep the amount of free space at some desired amount. And the result is a block allocation graph that looks much more erratic and much more frequent block allocations occur. And you can see as well the time between 2 allocations is also significantly decreased. So as for some numbers, what I've presented here is for 2 different storage media size, 200 megs and 2 gigs. The first row corresponds to the results without using ballooning at all, just running our simulations normally. And as you can see, as we increase the amount of ballooning, the metric that I used to express how much we did is called the fill ratio, which is the percent of data that is considered valid on an erase block. So here at 80%, it means that if you go pick a random erase block, you'll find 80% of the data there is valid, which means that when you perform a garbage collection, you're going to have to copy 80% to somewhere else. And as a result, because of all this extra copying, the block allocation rate increases. Remember that for these file systems, data can only come from one of 2 locations. Either it's legitimate data being written by the phone or by whatever is causing data to be written, and this is fixed between experiments, or it is data that's being copied around because of the garbage collection measurement. And this is what causes the increase in block allocation rate, is all this extra copying of data. But the consequence is the deletion latency, of course, decreases quite significantly because we are now erasing these erase blocks more frequently. And in particular, it's well suited for the large storage media because with a very small increase in the block allocation rate, we effect a very large payoff in the reduction of deletion latency. The problem is that we still don't get a guarantee on secure deletion. In fact, to get this number much lower results in very, very high, the opposite trend occurring, so very high block allocation rates. So we'd still want to have this deletion guarantee. And of course, the logical answer is then to combine the two approaches. We perform purging periodically, for instance, once a day. And at all other times, we're just running some amount of ballooning that the user has decided. So when this was all determined experimentally, but for the 80% fill rate case, it was only 357 erasures required to purge all of the data on our storage media. And this is because most of the empty space was just filled with the junk files. We didn't have to fill them again and again each time we performed the purge. I expressed the cost of purging as well as by this block allocation rate per hour to do it once a day. So this is the daily purge add cost. So if we have an 80% ballooning rate, in this one case, it only costs an additional 14 block allocations an hour to be able to purge once a day. So yeah, in summary, I guess I can put this slide here so we can see it in comparison. Then the user has some sort of trade-off. They can choose, well, how much of their block allocation rate based on their actual load depending on how they're using the device, the daily purge add cost, and they can decide what would be suitable for their purposes. But this is in user space. Obviously, we can do better. We can do better when we can change the file system in any way that we want and have as complicated a solution as we choose. And now I continue the talk with the data node encrypted file system, or DNEFS, along with its implementation, UBIFSec. So the intuition of this solution is first that we have to erase blocks in order to securely delete data. This is in some way a sunk cost. There's no other way on flash memory to remove this data from the device. And as a consequence, if we're not performing batching, if we're not collecting erasures and doing them at the same time, then the result is that we have just the naive solution again. We delete a page, we perform a garbage collection of all the other pages, and then erase that erase block. And this is just the naive solution. So we have to do some batching in order to have any efficiency. The goal now becomes, how do we get the most value from each erasure? How do we maximize the ratio of bytes deleted? The solution that we've come up with is to encrypt each data node in the file system with its own key. And a data node corresponds to the minimum unit of I/O. So you can think like a flash page. So every flash page is encrypted with its own unique key. Then we take all the keys and we co-locate them in a different area called the key storage area, or KSA, which I'll be using frequently. Then we purge periodically this KSA to remove all the deleted keys. So we perform the naive solution there by copying the keys we want, by not copying the keys we don't want. And the idea is that the KSA is going to be much smaller than the actual main storage, so this is where we get our efficiency. So here on the right, we have the main storage. This corresponds to the existing file system entirely. It's a normal log-structured flash file system. It's not performing any secure deletion considerations whatsoever. It's just existing just as it was before. And of course, because it's a file system, it's divided up into some kind of minimum unit of I/O called the data node. And here we see that instead it's stored as encrypted versions of these data nodes. What we've added is this KSA. And this we do not treat as a log-structured file system. Instead, we're very careful to securely delete anything that we want from the KSA, and we do it using the naive approach. We copy the keys we want, we don't copy the keys we don't want. And as I mentioned before, the efficiency comes from the disparity between the size of the entry in the KSA and the size of an entry in the main data storage. So for the write operation, I'll walk you through write, read, and the purging. For write, we want to write this new data node, DN3. So the first thing we do is we find an unused key. K3 suits our purposes. We encrypt the data node. We then store it in some unused place, and we associate the key in some header. So it's written along with the header. We add to the header as well which key position was used to encrypt it. Of course, not the key itself, but just a reference to some entry in the KSA that we can then use later when we perform a read. So now if we want to read data node 1, the file system tells us where on flash we can find it. Of course, we read the encrypted version along with this key position. We then read the key, decrypt, and return the data. Now, one thing that I want to emphasize here is that the actual encryption of the data on the file system is not affecting the user's experience or affecting the file system in any way. It's equivalent to performing any kind of encoding technique just before writing it to the storage media. So you perform an operation from the boundary of the file system and the storage media. In this case, you can apply error correcting code, you can apply compression. Here we're adding encryption just as a way of encoding it. The keys are available in plain text on the storage media. We're not trying to protect the data by encrypting it. We're trying to reduce the amount of space required to then later on securely delete the data. To store the keys, we store them in this KSA. We also have a key state map that tells us which keys are considered used, unused, and deleted. An unused key is a key that has never been used. It's fresh random data that we can use to encrypt a data node. A used key is some key that currently encrypts a data node that we consider valid, that the file system says this is a key, or this key we need to decrypt valid data in our file system. And finally, a deleted key is one that has been used, but now corresponds to a deleted entry in the file system. We want this key out of our KSA as soon as possible to affect our secure deletion. So to perform this purging operation, the first thing we do is we read one entire erase block of keys into RAM. We then, using the information in the key state map, we prepare a new version by replacing the keys that we want deleted with fresh, unused random data. And then we perform an atomic update of the KSA block so that the new version appears. Now, of course, flash memory doesn't support atomic updates, so what we actually do is we have a logical interface to the KSA. When we write a new version of a KSA block, we write it to some empty location, and then as soon as it's successfully written, we securely erase the old version and update the pointer to point to the new version of the KSA. So after we perform this atomic update, only the new version of this KSA block will be available. Then we just proceed iteratively across all the erase blocks in the KSA. And you can see we also replace unused keys as well as deleted keys when we're compiling new versions. The final step, we just update the key state map, and we finish the purging operation. The data is now securely deleted, provided we have a basic computational bound on our attacker. So some common questions to this point is, well, how do we do encryptions? What's our IV strategy? What block cipher mode do we use? Why do we encrypt each data node with its own key? Why this granularity instead of another? Why don't we encrypt why don't we have fewer keys but larger data nodes? And finally, why do we replace both unused and deleted keys with fresh new random data? So I'll answer these questions. First, encryption. So we use one key each time once. So we don't use any IVs. We have each time we want to encrypt a data node, we take a fresh, unused key. We use AES, we put it in counter mode, we start the counter at 0, we encrypt it. And the reason this works, that we don't have to worry about IVs, is that the key lifetime is simply that, one, it's generated randomly, then it's used to encrypt one data node once, only once, it's the only thing it'll ever encrypt. Then it may be used many times to decrypt it, and at the end it's securely deleted. So in this sense, then since the keys are all random, and we'll never have to worry about actually reusing them in different locations, and thus not need to worry about IVs. Second, why do we encrypt each data node with its own key? Why not another granularity? In particular, why not the whole file? So I had already alluded to this in the beginning of the talk. The problem with encrypting the whole file is that we still need seek. We can't suddenly say, well, to use our solution, you have to no longer permit random access. There had been some proposals made in the past that were never implemented, but consisted of saying the first step is to encrypt the entire file and then write it to disk. And it seems hard to still maintain POSIX compliance without having a little more details about how you plan to achieve this. So for one, you could have it in ECB mode, but then you lose semantic security, and that's too important of a property to just say, well, to use ECB mode just to have random access efficient. One thing you could have is refresher IVs. So you permit random access by allowing fast seek to the middle of the file. You go to the nearest refresher IV. Many encrypted file systems perform this. The problem with this approach is then you can't delete part of the file. And some people have said to me, well, then why don't you just securely delete the IV? So I just want to emphasize there's no such thing as an IV you can securely delete, because these are by nature public. The keys are what are private. So as soon as you start imposing key storage requirements on IVs, then they become elevated to the status of keys. You could have a counter-like mode or a CBC-like mode with just one key per file, and then you just say, well, okay, if you want to modify the middle of the file, you re-encrypt the rest of the file. Or in the case of a counter mode, because of the two-time pad problem, you just re-encrypt the entire file, and you just have inefficient random access. What's interesting here, and our approach, they kind of are two endpoints on the same spectrum. So our approach is the minimum unit of I/O each gets its own key. And encrypting every file with its own key is just the other endpoint. So in our case, when you want to make a small change, you do no extra work. And at every granularity in the middle, you could have another solution the same. You could say, well, every 5 data nodes gets one key. And if you want to change one data node, you have to copy 4 data nodes perfectly and make your one change. And this is just a trade-off you could make in this space of possible solutions. At one end, 1 key per file. In our case, 1 key per minimum unit of I/O. But there's no reason why you couldn't have a different level of granularity. In fact, I've expressed the idea of this with this table. So here we have the size of the data node and the number of flash pages that it would consume. And the result is how big the KSA is, which I've measured in erase blocks per gigabyte, assuming some normal flash geometry. So if we have one data node per flash page, then we have a 64 erase blocks per gigabyte on our storage media. But the copy cost is 0. And the copy cost I'm measuring in erase blocks, and it's the amount of data that you have to copy verbatim just to make a small change to one part of a data node. So here in this case, if you say 16 flash pages per data node, then you have a very small number of KSA, only 4 erase blocks per gigabyte. This means you don't have to purge as many erase blocks when you're executing this purge operation. But anytime you want to make a small change to a file, you have to copy nearly a quarter of an erase block of data. So this is just a trade-off. We chose to implement it at the simplest level, 1 data node per file, because it made the actual fully implementing this to the open source UBIFS file system relatively straightforward. We didn't have to add a lot of complicated logic. It was very straightforward because the data node was already the minimum unit. But this trade-off does exist. So efficiency can result in just saying, well, I'm not doing random access too often. It's better just to have a smaller KSA. Finally, why do we replace both unused and deleted keys with new random values? So the reason that we do this is actually it's outside the coercive attacker model. So we have another attacker model that extends it, and it's to prevent an attack that could be caused by this attacker. So here, this is the attacker that we used in our Usenex paper. It's called the peekaboo attacker, which I don't get to say often enough. And it consists of an attacker who can perform a boo attack, which is the scaring you into revealing your secret keys and passphrases and compromising your storage medium, the general coercive attack. But they're also allowed to perform a peek attack at some earlier time. This could be, for instance, a state-sponsored malware that was sent suicide code when it was discovered, so they were no longer able to peek after the suicide code. At some point in the future, they might do a full compromise. You don't know. The idea, or perhaps it's just someone who happens to be able to get access to your storage media sometime, not fully compromising it, but happens to be able to read it. This would be considered a peek attack. And the idea is, first we divide the lifetime or the time into discrete epochs, purging epochs we call them. And then between the boundary of 2 epochs, we can perform some purging operation, in our case, purging the KSA. So the data lifetime consists of all of the purging epochs, starting from the full one from when it was written, and ending at the end of the last one when it was finally deleted. And of course, it would be a very nice security goal, if you could say, if a peek attack occurs before the data's lifetime and a boo attack occurs after the data's lifetime, or in any other combination of these that you want, as long as they're outside the set of purging epochs consisting of the data's lifetime, then the adversary would not be able to uncover the data. And as a result, this is why we update unused values. So here I have 4 purging epochs with 4 keys and their history. So K1 is actually created in purging epoch 2 and deleted in purging epoch 3. So the lifetime would be both of these purging epochs. And here K4 is only written in epoch 3. If a peek attack occurred in the first epoch, I guess it's a bit harder to see with the colors, but they would compromise all of these keys, and in particular K4 won't be used until for a few epochs later. And this is what makes it so devastating if we don't update these unused values, because if an adversary were to read them, they would know that every single one of these keys would eventually be used to encrypt important data. So we do it with replacement so that if the peek attack occurs, then instead they only learn what they can compromise in this particular epoch. So if it's outside of data's lifetime, they won't be able to compromise the data. So how do we actually implement our file system? So we used the UBIFS file system, which is a way of accessing flash memory through an interface called UBI. I'll just explain it quite tersely, but the flash memory here is at the bottom. These are all the erase blocks. UBI has a notion of physical erase blocks, or PEBs, and it has a one-to-one relationship with these. It instead exposes logical erase blocks, or LEBs. And logical erase blocks are really nice because they allow the actual content of an erase block to be updated. Not in place, of course, it'll physically be located somewhere else, but logically it's an in-place update. So UBIFS is a file system with a superblock always at leb 0. It doesn't matter where it's actually stored on the flash memory. UBI provides us where leveling, and UBI also provides us the ability to securely delete all the old copies of an erase block after we performed an update. So it gives us a lot of the features we needed for our implementation to make it pretty straightforward to do. We just added the KSA pretty much as I described. We changed the read and write functionality of the file system. I don't have time to go into the full implementation, but it's in the paper if you like the sort of systemsy stuff. But basically, UBI gave us all the legwork that we needed to do the implementation. We added, in UBIFS's compression, we added our cryptographic operations. It's just the way it was encoded before writing it to the storage medium. And yes, it's fully implemented. There's actually a branch I have on the author's Git repository where I've been submitting patches because he likes the idea and wants to incorporate it to UBIFS, which has been good fun. So we've tested it in simulations. We've used it as the main file system on this phone. And we were able to use the phone just fine. We played movies. It was working all nicely. We did some experiments to test what it would be like. Here is an example of using our simulation that we had developed in the first part of the talk. What would be the erase block allocation rate? For standard UBIFS, we saw about 21 erase blocks per hour. And then, as you can see, as we increase the knob of frequency of purging, this increases because we're performing a lot of extra purging of the KSA. Well, what I want to emphasize is that the 60 minutes means that the daily purge add cost is less than a single erase block allocation per hour. And this is just with the first implementation, obviously there's room for improvement, but it means that compared to what we could achieve in user space, this is vastly, vastly more efficient. And the lifetime in years is based on a rough calculation, but it seems to exceed the lifetime of the owner, so this is probably going to be palatable. For the throughput, we compared it against the standard UBIFS and also UBIFS, what was on the phone. And we wanted to measure the power consumption to make sure that it wasn't introducing wildly inappropriate amount of power usage just to perform encryptions. It wasn't. We were able to achieve reasonable rates for read and write throughput. These can also be improved as well. In particular, the reduction in throughput for UBIFSec is not because of encryption, but it's actually just reading the key from flash. So if you keep caches of pages of keys around, I mean, obviously there's security problems there that you'd have to take care of, but if you were, with some caching approaches, and also when you're performing purge, you generate new random keys, you can keep those around too, because you know those are the keys that will be used for all the new incoming data. You can improve both the read and write rates there. So I'll skip that. One interesting consequence of this design, and something that actually is also quite important to implement because otherwise it would result in a doubling of encryptions, is that it's pretty straightforward to turn this into an encrypted file system. Now, it's not an encrypted file system, of course. We're using encryption as a compression technique, not a security technique. However, if we just encrypt the KSA with some long-term key that's derived from a user passphrase, then suddenly an attacker who's able to read the KSA without the passphrase won't be able to then decrypt the data nodes. Right now we store the KSA in plain text. Turning it into encrypted version is relatively straightforward and comes at very little extra cost. And this is also, we note that it's much more efficient than having a second level of encrypted file system on top that not only encrypts the data once for secure deletion, then encrypts it again. Here we just need to encrypt the KSA to get our security. So in summary, I hope that I've showed that first, secure deletion for flash memory is not just overwriting it with zeros. It's not going to work. We looked at the status quo for the Nexus Android One phone, and we looked at what we could do in user space, what some user-level solutions could be. We evaluated them, and then we saw that if we can then change the file system entirely, we could have a much more efficient approach. We proposed DNEFS, and we implemented it as UBIFSec, and thank you for your attention.
Time for a few questions, if Joel could repeat the question.
Okay.
Just a quick question. When you started doing these tests, you said you used your phone, and then you said how big the hard drive was for the phone. But is it also related to how frequently this phone was used, or what kind of user you are? Like how frequently you receive SMSs and send them out and that nature?
Yes, so the question is, when I was performing the simulations, is it going to be dependent on how the user actually uses the phone? And yes, so in this, we don't have the amount of data that would allow us to do a proper user study. So we just had what we use the phone normally, and we sort of intuited that this could be considered normal usage of the phone. Of course, what would be more likely the case is that you have many distributions of users, and you pick which dot product of distribution types you would most likely fit into, but we don't have simulation results for that. But yes, it would affect basically the trade-offs. So every time I mention that there's a trade-off between this and this, it would depend on exactly who you are, how often you're using the phone. For instance, the data node side, are you going to be doing a lot of random updates? If so, then maybe it's more important that you have one key per data node. But if you're not, then the other approach works. So this would come more from the end users or people providing this as the actual product. What would be the optimal setting for these trade-offs? But yes, these trade-offs do exist, and they depend heavily on how you would use the device.
Questions for Joel?
So, like these phones, you have apps, and when you start them, they probably take up some temporary space while the app is functioning.
Mm-hmm.
So I guess assume if the app is sensitive, all temporary space that's allocated to it is also sensitive.
Yeah.
So, do you have any notion of how that is dealt with, like temporary space? Is it considered just a regular file?
Yep. So when I was doing these simulations, what I found most surprising is that the phone is just constantly writing even when it's idle. And this is what made me feel that it wasn't so necessary to have a bigger model about using the phone. We just turned on the GPS, we turned on Wi-Fi, and it would just be writing data all the time. Oh, I saw this network, I saw this network. It's tiny cache files that were deleted shortly afterwards. And it seems to be very noisy, and there's a lot of sensitive data there. Just knowing which wireless networks you saw throughout the day would be your location history in a very coarse but still usable way. Yes?
So you were talking about turning this into an encrypted file system. So I'm not sure how you can maintain the list of keys because you're repeatedly removing them. So have you thought about this? How you can maintain the list of keys that correspond to each? How can you create that list of the keys from the passphrase or whatever it is?
So the question is how to create the list of keys. Do you mean the state of the keys?
Yes.
Okay, so the state of the keys can be created in a number of ways. UBIFS has a checkpoint replay mechanism, so we integrated our solution with that mechanism, meaning that we checkpointed the state, and then we would read it, and the journal would update it. But in general, if you have a file system, it'll have an index. And if you look at every node in the index, and each one of these is able to say, my key is this position, then you just read this index and you have the full set of used keys. So there's a very natural consistency check you can then implement. You just look at what the file system believes is its current state of valid keys, and you make sure that your map is the same. If the KSA is encrypted, it's just the actual value of the key that is being encrypted. So when you want to compute, for instance, data node 1, it's encrypted with key K1, you would go to the KSA and you would read K1. In our solution, you'd then take K1 and decrypt it. But with the encrypted version of the file system, you would then get a key K1 encrypted with some constant master root key. And this master root key is kept in RAM, I guess, at all times, and it's derived from the user's secret. So this would affect secure deletion against a theft type of attacker, but not against a coercive attacker, because of course the coercive attacker could get our passphrase.
Okay, let's thank the speaker again.